Good morning everyone. My name is Capitan and I'm doing this presentation today on behalf of Professor Pedro Marron, who unfortunately could not make it today. So I'm coming from the University of Duisburg in Germany. We also belong to the VCTech Center, which is a virtual center in order to promote research on smart cities and the Internet of Things. So the talk today is about, I'm going to talk today about the challenges in the deployment and maintenance of the heterogeneous network of Capitan objects. Okay? So the main question today will be, are we ready to go large scale with these systems and this application? And the answer to that question, according to us, is that no. Okay? So nowadays, we think that there are still some technological gaps that we need to cover before going into large-scale applications for cooperating objects or smart cities. Okay? So during this presentation, I will try to convince you, and I will try to show the main trending topics these days and the main gaps that are currently being under research. So before starting, I would like to present here some preliminary terminology. As you can see in this picture, we have nowadays different communities working on cooperating objects for physical systems, robotics, and so on. And all of them are sharing a high degree of overlapping. Okay? So I just prepared here a couple of definitions, for example. So I'm reading to you for cooperating objects. What is cooperating objects? So cooperating objects are modular systems of autonomous heterogeneous devices pursuing a common goal, okay, by cooperation in computation, sensing, or actuating with the environment. However, these physical systems refers to the type coordination between computational and physical resources. Okay? These capabilities will be realized by deeply embedding computational intelligence, communication, and new mechanisms for sensing and actuation into physical systems. And finally, for the Internet of Things, we could say that Internet of Things could be conceptually defined as a dynamic global network infrastructure with self-configuring capabilities based on standard communication protocols where physical and virtual things have identities, visual personalities, use intelligent interfaces, and are seamlessly integrated into the information network. So what does it mean? That in the end we could say that all these different communities are converging to the same challenges. So they are like watching the same problem but from different points of view. Okay, so in this sense, cyber-physical systems are more focused on the integration between physical and software devices. Cooperating objects focus more on the notion of cooperation between the different objects. And for example, Internet of Things is more focused on the degree of interconnection, okay? So the idea there is to be globally connected. It's important to remark, I wanted to remark with this slide that in the end, the challenges for all the different communities are converging to the same thing. So there are a need for joining different people in different communities in order to address the same problems. So a little bit of summary. In this presentation, we'll talk first, the first part about the smart cities and some Internet of Things applications. In the second part of the presentation, I will talk about the main trends and gaps for cooperating objects research. And in the third part of the presentation, I will present briefly the Planet project. Okay, that is a project about cooperating objects that we are coordinating in our university. There will be also more presentations about the project. So first, before I start with the Internet of Things, it's important to have clear the idea of the amount of information that we have available for potential applications. So during that picture you can see the first, or the predecessor, the topology of the predecessor of the internet, the so-called ARPANET. Okay, it was just a few nodes connecting the universities of Berkeley, LA, and Utah, I think. And here, this is how this internet has evolved up to our days. Okay, so this is the topology that we have currently, and this is just to provide an idea of the difficulty and that we can face when we try to address all this information with our applications. Okay? So this graph here is called the height of Garnet. Okay, this graph is showing the expectations that we have along the time for the different emerging technologies. Okay, so this graph was first proposed by Garnet. Okay, and it's updated every year. So the idea here is that they think that emerging technologies has to go through different phases, okay, before we assume the mainstream adoption. So during the first phase, which is the technology trigger, what they call technology trigger, in that phase the potential technology breaks into the market, okay? There are some early proof of concept stories, and the media interest makes the expectations to be higher, okay? So then, during the peak of inflated expectations, we can see that in that phase there are some early publicity that produces a number of successful stories about the technology, and then it will come the through of disillusionment phase, in which the interest decreases, okay, due to some failures in experiments or due to some failures delivered in some of the products. Then during the slope of enlightenment, there are some more instances about how this technology could benefit or the enterprise, okay? So the technology also becomes more widely understood, and there are also second, usually, and third generation products in the market. And in the end, if the technology make it into the plateau of productivity, we can assume that in that phase, the mainstream adoption of the technology takes off, okay? So I put this slide here just to show that the Internet of Things and other related technologies are still, let's say, close to the peak of inflated expectations. We have these technologies that has emerged not so long ago. We have like many expectations about them, but still we are far from getting to the last phase of mainstream adoption. So this is like a lot of work here before we can cover all the different issues. So here, this is an idea of with a ubiquitous city, okay? So we can call them ubiquitous cities, smart cities. It's all the same concept, okay? So what is a smart city? So smart city is a special city in which they enable, let's say, the urban functions and services, okay, such as administration, traffic, crime prevention, fire prevention, fusing high-tech infrastructure and ubiquitous information available into the urban area. So the user can access the network from everywhere and without even being aware of being connected. And also we have the idea of adding some intelligence into the different services in the city. So for that, we use different kind of wireless technologies such as Zigbee, RFID, or Wi-Fi, and also applications very related to the Internet of Things, in which everything is sharing the same information, okay, into a seamless network. So the main question is, are those smart cities just science fiction or are they real? So I'm presenting here a couple of samples, okay? So we have these projects in the city, this is the new Seoul city that is being built in Korea. This should be finished by 2014, and okay, there is like a budget of $25 billion for this project. It's based on smart cards, RFID technology, etc. And as I said, it's under construction. Okay, you can see there are some pictures of the current state of the project, also some models of the final implementation for the city. Apart from this, this is just a short sample, but Korea is a pioneer country in this kind of technology. So here you can see an overview of the different projects running there about smart cities. There are like 22 smart cities right now in Korea, 14, 16 existing, and 8 cities under construction or with projects related to the technology. The main problem that they are facing right now is about interoperability. Okay, so there's a lack of common standards and common protocols for these urban services or big-use applications. So it's very relevant, it would be very important to address this issue before we can communicate as urban services that are running into a different city and then try to connect it to similar services in different cities, okay? So we also have some of those projects in Europe. I'm just showing here a small example that is the 22 project in the city of Barcelona in Spain. So here the idea was to take on us one of the districts of the city, okay, in this case the 6th Street 22. So the idea is to take one of these districts that was an industrial district and convert it into a smart city environment. Okay, so trying to connecting people, information, city elements using the different new technologies, such as I said before. The idea, of course, is increasing the quality of life and try to make the management and the maintenance of the different city services more efficient. Here you can see a plan of the area. Okay, so this is the district in red that they are covering, and they installed like an infrastructure network with Wi-Fi nodes, like 680, in order to connect all the cooperative services and sensors and different city elements. Okay, they are right now offering like kind of 20 services. So here, this is another sample of a potential application for smart city, smart city or an Internet of Things application. So this is a picture of the city of Rome, okay, during a concert of Madonna in the Olympic Stadium. So, and this is the mobile phone calls distribution that was recorded during an experiment in the concert. So the idea is if all of us are carrying our smart devices and we are able to share that information into a background network. So if we have available that information, we could use it for many potential applications, such as, for example, routes management or fire management, or wherever. So this is just to show an example of how important would be the interconnection and the sharing of all this information for the services of any city. So now let me go into the second part of the presentation, okay? So okay, I explained now some potential applications, the potential that we have with smart cities, with Internet of Things, or with cooperative objects. But now I will go through some of the main gaps that we have currently with the cooperative objects technology, okay? The different research trending topics and the difficulties that we can face when trying to apply these applications. Okay? So most of the information I will present now is extracted from this book. Okay, this is a book that was written by or edited by Professor Marron and some other colleagues. It's one of the main results of the CONET, that was a Cooperating Objects Network of Excellence. It was published by the European Commission and then is updated every year. And the idea is just it's an attention to be a state of art for cooperating objects, providing like guidelines about the current research topics and gaps and trends for this technology. So here we classified the different gaps or trends according to their importance in this axis and according to the time that we expect for them to be solved. Okay, some of the trends should be solved in a short-term period or in a long-term period. We also classify them into different categories. Okay, this is order, depending on the color. Also hardware-related trends, algorithms-related, those are those related to the non-functional properties of the cooperating object networks, and the ones related to the systems. So through in the following slides we cover all the different categories, and we will study a little bit more details about the main trending topics for cooperating objects. So here we will classify, let's say, those that we consider are more important and that should be solved in a long-term period. And here in this part we have some other important ones, but that we assume that are close to be solved. So it's something that more or less is running quite well. Okay, so some fundamental challenges. I'm gonna start talking about hardware-related problems for our cooperating objects. So here all the data I'm showing are extracted from a survey that was made with 80 experts in the field. So they were given a list of topics, of possible topics for cooperating objects, and they had to grade them in terms of importance and in terms of the time in which they thought those should be solved. So according to that, we're presenting some information here. That is the classification that the expert made on the topic. So you can see in hardware-related topics, power efficiency is considered to be highly important. So if we want to go into a large-scale application and we want to drop our nodes somewhere out there, we need to leave them for a long-term period there. So we need them to be autonomous in terms of energy. So we cannot go there every half a minute and change the batteries, that's obvious. So in this sense, they are taking now a lot of research in terms of energy harvesting. So this is like a way of how can I make a node, a device, autonomous in terms of energy. So it should provide its own or produce its own energy. That's the idea here. So for example, those are examples of possible hardware for cooperating objects. So when we are talking about a cooperating object, we can name robots or smart devices or even unmanned aerial vehicles, okay, UAVs. This is another example, a very well-known example for hardware. There is the Deluxe-B, okay? This is a sensor usually used for wireless sensor networks. And here some more features about this nodes, okay, developed to be, and this I mode 2, there is another one by crossbow. So those are small devices, so usually are used for wireless sensor networks. So they are very interesting for ubiquitous applications because we can leave them in the environment and they can get integrated in an unintrusive way. But the problem that they face usually, or one of the problems, is, as we were saying, is about energy. So those are some data about the power consumption of these devices. So it's true that we can use some power-safe modes of the CPU. We can try to apply some different tricks, such as when we are running our application, we can go into the sleep mode, try to turn off the radio or the sensors when we are not transmitting, so we can have an application in which the sensor is just off and just waking up every half an hour or every once an hour in order to send the information and then going off again. So all those tricks are of course for saving energy, but in the end we can just extend a little bit the life, but we could have it running for, let's say, a week or a couple of weeks depending on the application. But it would be very interesting to have, let's say, the node, the device producing its own energy. So this is what is this attempt in the energy harvesting community. So the idea is to take energy that is out there in the environment, try to harvest that energy and store it and save it locally in the device to be used later. So how can we get energy? So there are different sources. For example, light, okay, solar light. With solar cells, we can get energy that is stored. This technology is quite advanced these days, quite developed. But there are also some other alternatives. All of them are very well reviewed in this Paradiso paper. For example, we can extract energy from temperature gradients, also from acoustic noise, even from the vibration around, okay, when the device is vibrating, or even when devices around us are vibrating, we can get energy from that. We can also, there are some piezoelectric devices, for example, that takes advantage of the movement of a hill. So when we are walking, we are producing some energy, and we can try, there are already some prototypes that can extract and convert that energy into electrical energy. And also we can get energy through the air or liquid floats around the device. Okay, so now some more fundamental challenges for cooperating objects. This time, I'm gonna talk now about how to install the system or how to plan where to install it in simulation. So here there are gaps and trends related to what we call other category. Here, one of the main issues I would like to remark is about the standardization. Okay, I talked about it before. So this thing is still in the long term. Okay, so but it's quite important if we want to go into large-scale applications. So we need common standards, common protocols, in order to be able to interconnect different applications that are running very far away, but they might be connected thanks to the Internet of Things or wherever. So there are currently a lot of problems about interoperability when we go into large-scale systems. So all the experts are assuming that this will be a very important or relevant issue in the next years. So planning our network, okay, so when I talk here about planning, what I mean is where should we place the different objects, okay? So For that, we need to consider topology constraints, coverage constraints. We also need to take into account possible changes in the environment, okay, in the environmental conditions. And the installation, okay, of course, this is not a computer science problem, but it's also a relevant problem, okay? So, because we need to go out there, integrate our systems into the existing systems in a, let's say, non-intrusive way, and also we need them to be accessible for maintenance, okay? So it's important to consider all these issues before addressing the installation. I'm showing here some pictures of another possibility. This is the one we are addressing in our Planet project. Here the idea is, okay, I don't pre-install the network. I just go there and deploy it autonomously with some vehicles that I have. So I will talk about it a little bit later in the third part of the presentation about this project. Okay, so now to finish with these challenges, there are also some challenges related to network operation. Okay, so what do we do with all the amount of generated data? How can we address or deal with this data? How can we monitor the network? Or how can we design user interfaces that are adequate in order to deal with all this information? So here are the trends related to systems. We can see that more or less in the short term we already have a few operating systems that are functional and are already working for creating objects applications. However, we don't have so many debugging and management tools, which are also important and should be addressed in the close future. Regarding algorithms, most people are putting now more emphasis on the localization and the cooperation of mobile objects. So localization is well covered, more or less. So we are able to localize our devices. We have many algorithms, many technologies for doing that. But dealing with mobile objects is something still in the air, okay? Something still to be addressed. And it's becoming quite important in these days. Regarding the non-functional properties, apart from scalability, also security and privacy issues in the networks, most people mark as very important the reliability and robustness of the system. If we want to go into a large-scale application, we want to place our nodes out there and leave them for a while. We need them to be, of course, reliable in terms of hardware and instead in terms of software. Okay, so as I said before, there are some issues related to network operation. Just to give you an idea, okay, this is on the left picture you can see how it's an airplane, like at the beginning of the century, and this is how it's an airplane right now. So we can see the difference about the kind of information that the pilot has to deal with. So we have so many sensors, so many controls, so many information available, and that the idea is that I want to transmit here that it's becoming really difficult, really tough to be able to deal with all this information at the same time. To give you another sample, some more numbers. So there are like 2.9 millions of emails sent every second, okay? Let's say also like, for example, 50 millions of tweets every day. So we are on the internet generating a huge amount of information, even per second. We have all this if we have all this information available, we could achieve like many, I can think of many potential applications. But the idea is, are we ready to deal with all this information at the same time? Are even our devices ready for tackling that? Another sample, Eric Smith reported that every 2 days we create as much information as we did up to 2003. Okay, so this is just another sample to give you an idea of the amount of data that we are talking about and the complexities that can be related in terms of operating networks that are interconnected in that kind of world. So also there is another problem with the user interfaces. We will have like millions of embedded devices, ubiquitous, all of them interconnected, sharing all this information that could drive us even crazy, okay? So, for example, this is a joke that Professor Marron prepared for us about how crazy you can get if you try to follow all the rules, all the information that your smartphone is providing you, right? So now, network repairing and healing. The last idea here in this part is, once the network is out there deployed, I would like to be able to monitor, looking for possible or potential failures, potential breakouts in the network, and I would like also to be able to fix it autonomously. If I want to go into a large scale application, something that is going to be there for a long-term period. So the idea is being able to detect holes, failures in the system, try to make a non-intrusive monitoring technique, okay, for the network, because we don't want to increase a lot the traffic and then I could solve it, let's say, just by rerouting information through different paths, even by going there with an autonomous vehicle and then dropping or placing a new sensor in a place where other sensors fail. Okay, this is something that we are addressing also in our project that I'm going to explain now, okay? So now let me talk in the third part of the presentation about the Planet project. I'm going to introduce it just briefly here today, and there will be also some more presentation about the project, thing tomorrow. So Planet stands for Platform for the Deployment and Operation of Heterogeneous Network Operating Objects. It's an integrated project, okay, funded by the European Commission that we are coordinating from our university in Lisbon. This is the main approach, or let's say the main goal and objectives for Planet. So the main idea is to design and development and validate an integrated platform that is enabled or enabling the smarter deployment, cost-effective operation and maintenance of large-scale complex system of heterogeneous network operating objects. So we will work with wireless sensor networks, also actuator networks, and mobile objects such as robots or aerial vehicles. So therefore, the objectives are the design and development of the platform, the communication framework for all of them. Also, the methods for network deployment and network-centric computation, and also working on security methods for our network. Regarding validation, we have two different facilities for Planet. So in the first one, we are going to test the platform in applications related to environmental monitoring. Okay, this is the testing facilities. We are going to go to a biological reserve, this Doñana, in the south of Spain, one of the most important ones in the south of Europe. And we are going to test their applications related to pollution, monitoring of the water, monitoring of animals. I will go into some more details now. Then we also have a different facility. We're going to test our algorithms in a new UAV airfield facility that is being built right now, also in the south of Spain. And this will aim to be an autonomous airport for UAVs, and it will be used for researching on air traffic management and UAVs in general. So we will test here applications related to critical infrastructures, critical communications for UAVs and vehicles in general. Of course, there are some other case studies in which our Planet approach could be tested, could be used for search and rescue applications and robotics, also for forest monitoring, for example, but all these are studied or tested in other similar projects, but will not be addressed here during our project. So some data about the projects. As I said before, it's an integrated project funded by the European Commission. It's a 4-year project, and we are now just starting the last year of the project. So we have some many preliminary results. I will show you some video later of the experiments that we perform in Doñana. It's a total budget of almost 7 million euros. And here I would like to highlight the fact that we managed to have a nice mixture here of academic and industrial partners. So the idea is not just developing the algorithms, testing them, but going into a final system. And for that we need also, of course, always the input of the industrial partners. Some of them are working in very related technologies and have a better knowledge of the market. So this is the main approach in Planet. First, we will have a user that is the one in charge of providing the specifications. Okay, so we want to perform an application. The user is saying which kind of application I want to perform, which is my area of interest. And to the field for that, we have also a visualization center that will also play a role of user interface, user-machine interface. There we can show all the information online that is available for the system from the different sensors and from the different cooperating objects. And the user is able to interact with that information and try to command and control the system. Then once the user has specified which is his objective, his idea, then the system should be able to provide autonomously a plan for deployment. So plan for deployment is where should I place my network or my cooperating objects in this case. So I create a possible or a set of possible deployment plans, those plans can be optimized and validated through some simulation phase, okay, before going into the field. Then once I have selected which is the best plan, I can go into the deployment phase. For that, we will use like different mobile objects that are able to carry and deploy different sensors. And finally, once the network is deployed into the field, we will use some techniques for monitoring the network and also trying to heal possible failures or possible breakthroughs of the network. This is the plan architecture. Here, as I said, is where the user application would be placed. Okay. The planet visualizer is the plain double role because it's used as a user system interface and also as a visualizer. So it's connected to all the different data that are in the cloud, in our cloud, through the planet framework, and it's accessing to all the information related to any of the cooperative objects in the system. Then we have another module that is the planner. This module is very important. It's the one in charge of computing the different plans for deployment. So once the user is providing the requirements and depending on the application, the planner will compute the plan, as I said before, and then we'll try to simulate some, because sometimes we have different positions for the nodes that we want to test, or there are some features in the network that we can adjust, like for example, power transmission or some of the links. So we have some small parameters that we can tweak in our network, and we can simulate them and try to see which is the optimal approach. Then we have this module that is the planet control. This module is the one in charge of controlling all the different cooperating objects. This is done in a distributed way, so we will have different controls running on the different cooperating objects. The idea is that the controller is receiving a plan, okay? So you should deploy the network in such a way, and then the planet control is in charge of executing that plan and commanding the different COs to the different positions, dropping the different sensors, and commanding in general the objects. So in Planet for cooperating objects, we are working with UAVs or manned aerial vehicles, also UGVs, ground vehicles, and wireless sensor networks in general. So we have static wireless sensor network, we have also mobile wireless sensor networks, and we have devices to deploy and even to recover sensors from the environment. So this is an overview of the scenario in Doñana, just to show you the main interest of this scenario. This is a very heterogeneous scenario environment. We have like around the park we have like different small towns for agriculture. So we have some parts with irrigated crops or or agricultural areas. And we also have some part with active dunes close to the beach. This is the sea, okay? And we also have a fluvial marsh, that is a place that gets flooded depending on the season and can be very difficult to access. So in general, we have here like a merge of human areas and natural areas in which there are no humans at all, but only animal species. So also depending on the season, the level of flooding in the marshlands can be different. So this is just the motivation of why we cannot go there and pre-installed a network and leave it there for the whole project. So depending on the season, there are some places that are accessible and some places that are not. So we need to be able to deploy and then to recover the network autonomously. So, of course, before we arrived, and there were some infrastructure already in the park. This is used by the biologists working there to study some animal species and for monitoring purposes. So there were some stations installed in different places in the park. They were connected with some communication network, and they had also some databases centralizing all the information and all the data that they are recovering with their sensors. So the first idea in Planet, or the first step, was to try to integrate the infrastructure that they already had into our Planet framework. So the idea is being able to communicate all these infrastructure with the other systems in our platform, so that all this information from the databases and from the sensors is available for all the different objects that we have. So we want to take advantage of this pre-installation that they have and integrated into our system. Okay, so here I listed some of the applications that we are performing in Doñana, some samples. I will give you now more samples that the biologists were interested in. Pollution monitoring for the water, or monitoring of some specific animals, or transmission of diseases. Also, they want to use the aerial vehicles for making documentaries about some of the animals, and even for analyzing the area stratification of bats and insects. So we developed a device in one of our airplanes in order to capture different insects when flying, and then being able to analyze it in the lab after the flight. So first, I'm going to talk a bit about some of the applications, okay? First, about pollution monitoring. So why do we want to monitor the pollution of the level of the water? So this was, when we were right there, that was very interesting for them, because that could happen in some different situations, like, for example, episodes of water pollution due to pesticides from agricultural activities in the environment, also due to untreated water from nearby towns in the environment. I showed you before that the bar is surrounded by some small agricultural towns, and also due to toxic algae blooms. Okay, so all these cases can produce like different pollution events in the water. Unfortunately, the risk of these events is not low, and it has already happened in the past. It's, like 10 years ago, there was like a big pollution event in Doñana, in the park, and it caused like a mass mortality in different species of fish and birds. Those are protected species, so the importance for the biologists to be able to control all the time the level of the pollution in the water is crucial. This is why this is one of the applications in the project. So why is this application challenging? So the scenario is a very large scenario. We're talking here about square kilometers in the area. Some of the parts are very difficult to access, mainly the marshland, because we cannot access there by foot, only on horse, and only in some periods, during some periods. And we have this large then scenario. We have like a limited set of number of sensors to cover the area, and we need to get global information from the environment and also detailed information on some specific points that are the points in which is more likely to happen one of these events. So it's difficult to cover this space, and we need to add some flexibility into the system. So this is why we will use mobile sensors in order to cover different areas at different moments. We will use also this tool for deploying sensors autonomously depending on the requirements. And then we will also be able to recover a sensor that we deployed because maybe it's not needed there anymore, or maybe because we need to perform some healing operation in the network. So in summary, the functionalities that Planet will be providing, and some of them are related to this application. We will make surveillance with the aerial vehicles. So the idea is to mount some cameras on the vehicle, go with the airplane, and just fly over the area in order to survey which is the situation of the environment, let's say. Also, we will perform deployment of the wireless sensor network with the UAVs, as I said. We will do that with helicopters and also airplanes. We have different deployment tools for each of them. Then we will perform data collection in wireless sensor network with the UAVs. So here the idea is, okay, I deploy the sensors and then they are like very far away. They cannot even connect to each other. So what can I do with the data? So the idea is I go to the UAV, I fly over the area where I deploy the sensors, and then I wait until they send me all this data. So the UAV here is working as a kind of data collector. So we use it as a data collection station, but it's mobile. So we can fly over different areas and we can recover the data from different clusters of nodes that are not interconnected.
So you make a request to the nodes that they...
Depending on the application. Usually some of them are just, let's say, communicating among them, making clusters, and then they just wake up every, let's say, half an hour or whatever, and then they detect or they send a beacon to see if there is any data collector around. If the UAV is detecting the beacon, then it's replying to the nodes, like saying, okay, I'm here, and then is when the nodes are transmitting the data. This is just for energy saving, of course, because they cannot be all the time request, and they cannot be all the time.
Use the vice versa protocol with LPP, so you can send to them in order to wake them up, so that there is a response to you.
They also can do that. So it's like, yeah, so we are trying to test their different protocols, okay, in order to make it, let's say, more efficient, so that they don't need to. So one of the research topics there is about that, specifically about trying to find an optimal protocol for the and finally pollution sampling using area vehicles. This is something that is done the DLR in Germany, the Centar. So they developed a device for taking water samples with the helicopter, so they can fly, then get low in close to the water, sample some water into a tank that they have, then fly back and take that sample to the lab in order to be analyzed. Okay, so planning, how is this done? Just a little bit of an overview. So as I said before, the user is providing some requirements. In this case, it's like saying a description of the area of interest that he wants to survey. Then he can also provide some parameters like the kind of cooperating objects that are available and the hardware that is available for each of the cooperating objects. And according to all those parameters or features, the planner will be able to provide a deployment plan. Okay, like deployment plan is for the mobile objects is like a route, a list of waypoints they should follow, or a list of waypoints where they should place some different nodes in order to cover the area. So we can have like different kinds of plans. So the objective here is to minimize the number of sensors in order to achieve our required coverage. So we have some requirements, we want to achieve those requirements, but we want to, of course, optimize the number of sensors. And of course, we will have some model of the sensors, of the coverage, and additionally, we need to take into consideration some geographical irregularities or sensing events. For example, there are some areas in which the nodes cannot be placed or because they are not accessible. There are also some areas in which the events that we want to sense are more likely to happen. So all these different options should be taken into account into the planner. So as I said before, the goal is to deploy the static and mobile sensors in order to meet the requirements about sensing coverage, network connectivity, and even data collection. So I should be able to deploy the network to cover all the area of interest, or at least as much as possible. I should be able to collect the data of the sensor later, and of course I should be able to connect everything together. So we are working on two different strategies, one for a set of strategies for static wireless sensor networks and a set of strategies for mobile sensor networks. Here I'm showing a small example, okay? So this is the same scenario but covered by static network and by a mobile sensor. So here if I have a static network and I want to cover all the green area because the red area should be something not accessible, then I can place different nodes at these points and cover all the area. However, I could do the same with a mobile sensor just by providing a list of waypoints where the sensor should travel or fly or driving in case of a ground sensor. So if the sensor is going through all the different points, it's taking information from the different points. Of course, the difference here is that all the measurements are not correlated in time, and there the measurements, we can have them synchronized in time, so we can be sensing different places at the same time, something that we cannot do here. So this is why it's a good idea to combine the static part of the network with the mobile part of the network. Another application here in the Llana is about the horse monitoring. Okay, so also the biologists there in the park were very interested in monitoring and certain groups of animals. In this case, the certain kind of wild horses there. So they want to study, or they are studying kind of behavior of these horses. So for that, they want to study where they live, usually the kind of groups that they make when the migration movements that they have, where do they move and when, depending on the season. So in order to track the horses, the idea here is to mount some non-intrusive sensors on the horses, so that we can sense their positions, we can track them, and we can log that information. And also, second idea is to install some ground data collection stations, some specific points where the horses are usually nearby, and then with those data collection, we will use them to recover the data from the sensors. Of course, as I was explaining before, we cannot place data collection stations all around the park. Just a few of them in the places where they are usually living. So we will also use the UAVs there as data collectors. Okay, so we can use the UAV with the camera first to fly and survey the area and detect where the horses are, and then we can go with the UAV and try to apply different protocols to recover the data from the sensors.
Do you have any specific protocol for traffic patterns? I mean, by night, for example, they are sleeping, so in order to not preamble or something all the time with the medium?
Not right now. I was going to say in these sensors are different because those sensors need to be there mounted and working the horses during usually 1 year or almost 1 year, because those horses, they just grab them like twice a year and then they mark them. So this is the only possibilities that we have to place the nodes. So therefore these nodes, the ones on the horses, are just sleeping all the time, and they wake up. I think they have this is being done by people in Edinburgh, in the University of Edinburgh. I think they have like a protocol in which they wake up the sensors once an hour, and then they try to send the information. But all of them are synchronized. So the idea here is that we need, well, in the first approach, they are all synchronized. So the idea is that we need to go to with the UAV being flying over the area for a while until we, let's say, meet the time slot in which they send the data. So this is why we need to fly on circles of the area.
Because there are signal projects where there are animals and penguins or storks, and they are flying away, so it's hard to go there to gather the data so come back. So there are other ideas to make them to exchange the data between each other, data dissemination, so that when they will come back, so you will be able to gather the information from several of them to the rest of the group.
Yeah, of course. We are studying. That is an open issue for us right now, because we are studying also the possibility of having each of the sensor sending a different time slot, so that we can gather always information when we fly on a sub-protocol in which but I think there are some hardware constraints so that they cannot change information among them, the different sensors. So, because they cannot be listening and sending at the same time, so this is a constraint there.
So that's why it would be nice if you switch to a synchronous protocol, sort of synchronous. Right.
This is one of the ideas that we have, like having a different time slot for each of the sensors, so at least, because if they are usually moving in groups, so if you know where is one of them, at least you have a rough idea of where the others are. So this is one of the options, but it's not implemented yet in the experiments we have. So this is an example of the collars that we mount on the horses. Okay, you can see they are not very intrusive for them, and they are light, not very heavy. This is the hardware in one of the sensors. So the more important part, of course, the most important part is the GPS and the accelerometer sensors, because what we want to track is the position of the horses. And so this is the last application I am explaining today here in Planet. This is about environmental monitoring. So in many cases the biologists are very interested in knowing or measuring some features in the environment, okay? Like and they are interested in measuring the spatial or temporal distribution of different environmental factors such as the temperature. So for that we need some sensors, and the idea was, okay, if we are mounting these sensors into the horses for measuring, for tracking their position, why not using also these mobile sensors in order to sense, for example, temperature in the environment. So we would have like a set of mobile sensors that we cannot control, because we cannot control the movement of the horses, but we can use them to measure a different position of the part and try to rebuild a field of the temperature, for example, or some other factors. So the objective here is to take advantage of the wireless sensor networks that are already deployed for other purposes and try to interpolate the measurements that we gather at different places in order to reconstruct a spatio-temporal view of some vector field. Also, we want to estimate which is the error that we are making when we do that interpolation. So using the wireless sensor network for environmental monitoring has some advantages and some constraints. Of course, using the wireless sensor network is cheaper and easier to maintain or deploy than other systems that we need to be there, any other infrastructure that we need to have there pre-installed. We can also cover possibly larger areas because of the moving sensors and small devices. But on the other side, there are some challenges here because all the measurements that we are taking are, let's say, dispersed. Okay, we are dealing with a very large area, and we are just using a reduced set of sensors. And the measurements, as I said before, might be delayed because by the time that we receive the measurement, we might have gone with a UAV, then recovered the measurements, so we are not getting information updated online all the time. And
sorry, in case of environmental monitoring, this should not be an issue since these parameters are not changing, so unless you are transmitting some kind of alarm.
yeah, of course, that's the good part. If there is something which the time dynamics is not very high, we can deal with that problem easily. We can also stamp the messages, so when we receive them, we can assume, okay, we can know that measurement was just taken like a few minutes ago, so that's not a problem, and we can try to synchronize also the measurements with that. So what's the approach? The approach is we have a set of sensors there in the area moving, and the user maybe wants to make a request to know, okay, or to update what is the state of temperature or whatever factor, whichever factor is measuring. Then the system should be able to communicate all the different measurements and process them in order to interpolate, because we are just measuring at some specific points, and maybe we want to know what's the state here in these other parts of the environment. So the idea is to take into account the measurements, the samples that we have, and try to interpolate the state in other different places. For that, we're going to use, we're studying the use of different techniques for spatio-temporal interpolation, such as Kalman filter or Bayesian regression or Gaussian processes. So those are statistical tools in which we can try to minimize the error that we are committing when interpolating our variables. Also, we would like to do that in a distributed or scalable approach and try to compute at different places, different estimation. Okay, so here I'm almost finishing. I would like to show you a video of the experiments that we had in the Llana. So here you will be able to see some of the experiments that we performed in the Llana during, I think not last year, but the previous one. So the images are taken by the aerial vehicles. So you can see that this area is the one I was mentioning, the marshland, but it's very difficult to access, even by the biologists. As wireless sensor network, we are using the Deluxe B nodes, also some specific nodes for measuring the water pollution. They are being developed by the people in the University of Edinburgh. Those sensors are not that light like the Deluxe B, so they need to be. We can just carry one of them each time with the helicopter because it's like a medium-sized deposit or tank, because they need to take some samples of the water. And this year in September we are doing some more experiments there in the field, and we will try to deploy the water sensor and also to recover the UAV. Okay, so let me just finish the presentation with some brief conclusions. So as a summary, I talked to many different technologies, okay, like cyber physical systems, cooperating objects, or the Internet of Things. So the idea I wanted to transmit is that, okay, all of them, if we want to go into large scale, we are facing kind of similar challenges or similar issues. So the idea is that all the different communities working in robotics, computer, cooperative objects, and so on, should work and are starting to work together in order to solve these issues. And also, the second thing I wanted to highlight is the huge amount of information that we need to process for this application. So in a near future, we keep increasing this amount of information. We will need to start thinking about how can we deal with all that information because we have available more information that we can even process with our devices. We are going into smaller and smaller devices and we are going into larger and larger amounts of information. So that is also an important issue. I also pointed out the lack of standardization that we have in all these technologies, okay, which is very important for the large scale approach. Also scalability, mobility, reliability are major issues that are indeed under research these days before going to the large scale fashion. So I finished with the same slide I was presenting at the beginning. So I hope it's now more or less a bit clearer why there's a lot of work ahead before we move our Internet of Things and related technologies into the mainstream adoption, okay? And the answer to the question, are we ready to go large scale? As I said before, we think the answer is no, but we are getting there. So it's clear that the main trending research topics these days in cooperative objects and smart cities and so on, most of them are, let's say, led into this direction, okay, the direction of becoming or being able to address large-scale scenarios. Okay, so thanks for your attention, and we are finishing here unless anyone wants to add any more comments or questions.